Hello my friends and business partners from around the world. My name is Rafael. I'm an electrical engineer here in Brazil, and on this video I'm going to be speaking about complex numbers. Do you know what a complex number is? If you want to find out, continue watching this video. Complex numbers. Complex numbers are mathematical entities that are said to have a real part and an imaginary part. They are oftentimes represented by the letter Z. Z with a dot on top is equal to x plus j y. However, we don't always use this representation. We use what's called the polar form of the complex number. The magnitude of the complex number in a phase. This phase is going to represent the shift from the real axis. This is the Cartesian representation of the complex number, and this is the polar form or the polar representation of the complex number. Okay, before we talk about the polar form of the complex number, we will understand the Cartesian form of the complex number. The Cartesian form of the complex number has one number which is real. It belongs to the real set of numbers, or if you prefer, the real axis, and the imaginary part is the part that belongs to the imaginary set of numbers, or the imaginary axis. Okay, why imaginary numbers? Do you have to imagine something? No. Imaginary numbers are not something that only exist in your imagination. Not at all. They are very real. Okay? I am an electrical engineer, and I'm going to be speaking about the definition that we have and the concepts that we have related to electrical engineering. In electrical engineering, a motor can be represented by an impedance like this. There is a real part and an imaginary part. For example, machines need magnetization to operate, okay? Without magnetization, without magnetic fields, the machines are not going to operate, electromechanical machines. And the magnetization process, the magnetic field, is not represented by a real number because it doesn't cause work in the real world. It is there only to magnetize the machine, and this magnetization is represented by an imaginary number, alright? Okay, but where imaginary numbers come from? Take a look at this function. F of x is equal to the square root of x. If we use a positive number, any positive real number, f of 4, which is going to be the square root of 4, we find 2, and 2 we know belongs to the real set of numbers. However, what if I put a negative number here? F of minus 4 is going to be equal to the square root of negative 4. I don't know. I don't know the number. What I do know is that this does not belong to the real set of numbers. Okay, to deal with this problem here, to the square root of negative numbers, mathematicians defined a number which they called I. I is the square root of negative 1. But I am an electrical engineer and I'm not going to use the representation that is preferred by mathematicians. I am going to be using the definition that we electrical engineers use, which is J. Okay? So J is the square root of -1. And how about in this representation we put the square root of -1 first, and then we multiply it by any kind of number. J times 2, or J2, is 2 times the square root of -1, which is gonna be, I'm gonna put 2 inside of the root. It's gonna be 4 times -1, and here it's gonna be the square root of -4. Okay, then using the definition that mathematicians like to work with, we know that the square root of -4 is J2. Okay, all right. Okay, but you tell me which one of the representations I'm going to prefer. It depends on the operation. Let's do some additions and subtractions. Imagine a complex number like this, and another one one plus J2 and 3 plus J5. If I want to do addition or subtraction with these complex numbers here, and they are in the Cartesian form, it's going to be very easy to operate this addition. Z1 plus Z2 is equal to, we simply add the real parts and we add the imaginary parts. So, performing addition and subtractions with the Cartesian form of complex numbers is very easy. It's extremely easy. However, if we want to do multiplication and division using the Cartesian form, it's going to be a little bit harder. Then what I'm going to show you is that doing multiplication and division using the polar form is going to be a lot easier for you. Let's take the same complex number and do multiplication with them. Z1. No. Because it's going to be hard. It's going to be hard. What we need to do is to have the polar representation. Z1 okay, these are two different complex numbers using their polar representation, and what we're going to do is to perform multiplication and division. What we do is to simply multiply the magnitudes of the complex numbers. 10 is the magnitude of this complex number, and 5 is the magnitude of this complex number. 10 times 5 is 50. And with the phases, we add them. We don't multiply, we add the phases. 30 plus 25 is 55. This is how we perform multiplication of two complex numbers. And how about the division? It's gonna be the division of the magnitudes. 10 divided by 5 is 2. And we simply subtract the phases. 30 minus 25 is 5 degrees. Okay, And in this way here, we were seeing that performing addition and subtraction with the Cartesian form is much easier, and performing multiplication and division with the polar form is a lot easier. Okay, so if you are given the Cartesian form of the complex number, you might want to convert it to the polar form in order to operate division and multiplication. And the opposite is also true. If you are given the polar form of the complex number and you want to do addition and subtraction, instead of using the polar form to do addition and subtraction, what you need to do is to convert it to the Cartesian form before operating the addition and subtraction. Now that we've seen this, what we need to do now is to understand how we're going to convert from one form to the other. To understand how we convert from the Cartesian form to the polar form, let's pay attention on this graph. We know that complex numbers can be represented in the Cartesian form and with the polar form. These are the coordinates of the complex number in the real axis and the imaginary axis, and this is the magnitude of the complex number shifted by an angle from the real axis. Okay, the complex number is simply a dot in the complex plane. It has a real coordinate and an imaginary coordinate. What we want is to convert to the polar form. To do this, I draw a magnitude here. This is going to be the magnitude of the complex number, and you see that it is shifted. It is shifted from the real axis. Alright? Now we can convert one into the other. See that we have a right triangle here, and the magnitude of the complex number is the hypotenuse of this triangle. We can simply perform Pythagoras. Okay, can you see that we can perform Pythagoras here and easily find the magnitude of the complex number? And how about the phase? The phase is going to be equal to the inverse tangent of the division of the coordinates y divided by x. Using these expressions, we can convert from the Cartesian coordinates to the polar form. Alright, now how we do the opposite? To do the opposite, what we need to do is to understand that if we have this, and want to find this, we can simply do this thing here. See that this is the hypotenuse of the triangle. If you multiply it by the cosine of this angle, you have x. If you multiply the hypotenuse by the sine, you have y. So this is how you convert from one coordinate into the other, and you do that, as we observed, Because we want to convert into the other, because for this coordinate here it's easier to do multiplication and division, and this coordinate here it's easier to do addition and subtraction.